The morning of December 16th, 1944 brought American artillery officers at Bastogne face to face with a technological miracle they barely understood. German forces had surrounded the 101st Airborne, cutting supply lines and threatening to crush the undermanned defenders. Artillery was the only thing keeping waves of German infantry from overrunning American positions, but conventional shells were failing in ways that made seasoned gunners curse. The problem wasn't accuracy. American gunners could drop rounds within 50 yards of their targets consistently. The problem was timing. Traditional artillery shells used one of two fusing systems, and both were catastrophically inadequate for the kind of fighting erupting around Bastogne. Contact fuses detonated on impact, which meant shells buried themselves in mud or snow before exploding, wasting most of their fragmentation effect underground. Time fuses required gunners to calculate exactly how many seconds the shell would fly before reaching the target, then manually set a mechanical timer on each round. Get the calculation wrong by half a second, and your shell exploded harmlessly above enemy positions or plowed into the ground without effect. Against massed German infantry attacking across open ground, American gunners needed something impossible: shells that would sense when they were directly above enemy troops. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today, and detonate automatically at optimal height, roughly 50 feet up, where the fragmentation pattern would shred everything below. That technology didn't exist in any army's arsenal. Except it did exist, and American gunners at Bastogne were about to use it without knowing they were firing the most closely guarded secret of the war, more classified than the Manhattan Project, more revolutionary than radar. The device that made it possible had been designed by a civilian engineer who'd never touched a weapon before Pearl Harbor, a man who solved the unsolvable problem of building a radio small enough to fit inside an artillery shell, rugged enough to survive being fired from a cannon at accelerations that would pulverize most electronics, and reliable enough to work in rain, snow, and temperatures ranging from -40 to plus 120 degrees Fahrenheit. His name was Merle Tuve, and the proximity fuse he created would kill more enemy soldiers than any single weapon system developed during World War II. But in 1940, when British intelligence first shared the concept with American scientists, the project seemed like engineering fantasy bordering on black magic. British desperation created the opportunity that would eventually revolutionize artillery warfare. By the summer of 1940, the Luftwaffe was pounding London nightly during the Blitz, and Royal Air Force fighters couldn't stop the bombers. British anti-aircraft guns fired thousands of rounds skyward each night, but hitting fast-moving aircraft at altitude required impossible precision. Gunners had to visually estimate range, calculate the bomber's speed and direction, set mechanical time fuses on each shell, and hope their mathematics matched reality when the round exploded. The hit rate was abysmal. RAF records from August 1940 showed that British anti-aircraft batteries were expending roughly 20,000 shells for every German aircraft destroyed. The ammunition costs alone were crippling Britain's war economy, and the psychological impact of watching bombers pass untouched through walls of exploding flak was destroying civilian morale. British scientists at the Telecommunications Research Establishment had been experimenting with radio proximity fuses since 1939, devices that would use radio waves to detect when a shell was near a target and trigger detonation automatically. The concept was theoretically sound. A tiny radio transmitter inside the shell would broadcast continuous waves. When those waves bounced off a nearby aircraft and returned to the shell, a receiver would detect the reflection and an electronic circuit would fire the detonator. The practical problems were overwhelming. Vacuum tube technology in 1940 required bulky, fragile components. The smallest radio transmitters available needed components the size of a shoebox and required stable mounting and careful handling. Cramming that technology into a 5-inch artillery shell that would experience 18,000 times the force of gravity during firing seemed physically impossible. The acceleration would shatter vacuum tubes, snap circuit boards, and destroy any conventional radio assembly within milliseconds. British engineers had managed to build experimental proximity fuses by late 1940, but they were so unreliable that only 1 in 10 actually functioned after firing. Churchill's government realized they needed American manufacturing expertise and research capacity. In September 1940, the Tizard mission arrived in Washington, carrying Britain's most sensitive military technologies, including cavity magnetron designs that would enable microwave radar, jet engine specifications, and documents detailing the proximity fuse concept. The American scientific community's response was mixed. Some physicists dismissed the idea as impractical. Others recognized the revolutionary potential but doubted anyone could miniaturize radio equipment enough to fit inside a shell. The National Defense Research Committee, established just 3 months earlier to coordinate American weapons development, assigned the Proximity Fuse Project to Section T, a division focused on advanced fire control systems. Section T's director was Merle Tuve, a 40-year-old physicist who'd spent the previous decade studying nuclear physics at the Carnegie Institution in Washington. Tuve had never designed weapons, never worked with explosives, and had no military background. His expertise was in radio frequency, physics, and precision measurement instruments. He'd built some of the first equipment used to measure the height of Earth's ionosphere by bouncing radio signals off the upper atmosphere. That experience with radio wave propagation would prove critical, but nobody knew it yet. When Tuve examined the British proximity fuse designs in October 1940, he immediately identified the central problem. British engineers were trying to adapt existing radio technology to fit inside artillery shells. That approach was doomed. The shells were too small, the forces too extreme, and conventional components too fragile. Tuve proposed starting from scratch with a radical constraint. Design the radio to fit the shell, not the other way around. Every component would be custom-built for a single purpose, surviving the violence of artillery firing while remaining functional. The War Department approved Tuve's research program in November 1940 and AZTF, assigned him laboratory space at the Carnegie Institution, plus authorization to recruit engineers from universities and private industry. Funding was modest initially, just $170,000 for the first year, because Army ordnance officers were skeptical the project would produce anything useful. Tuve's team started with the vacuum tubes, the most fragile components in any radio circuit. Standard vacuum tubes used thin glass envelopes containing delicate wire filaments suspended on springs. The acceleration from firing a shell would snap those filaments like breaking spaghetti. Tuve contacted Raytheon Manufacturing Company and explained the problem. He needed vacuum tubes that could withstand 18,000 Gs while remaining operational. Raytheon's engineers thought he was insane, but they agreed to try. The solution emerged through brutal trial and error testing. Raytheon's team designed miniature tubes using steel envelopes instead of glass, with filaments made from tungsten wire thick enough to resist the shock. They tested prototypes by mounting them in artillery shell casings and firing the shells from cannons at Aberdeen Proving Ground. Most tubes shattered. Some survived firing but wouldn't conduct electricity afterward. A handful worked perfectly. By March 1941, Raytheon had developed tubes designated the VT numbers that could survive firing and operate reliably for the 8 to 15 seconds a typical artillery shell remained in flight. Each tube measured just 1.3 inches tall and half an inch in diameter, the smallest functional vacuum tube yet manufactured. Tuve's team needed 4 tubes per fuse, 1 for the transmitter, 1 for the receiver, and 2 for the electronic triggering circuit. The next challenge was the antenna. Radio transmission requires an antenna proportional to the wavelength being broadcast. Tuve's team calculated that their transmitter would operate around 180 MHz, requiring an antenna roughly 3 feet long for optimal performance. Obviously, they couldn't attach a 3-foot antenna to a 5-inch shell. The solution was elegant. Use the shell's metal body as the antenna. By carefully positioning the transmitter circuit near the shell's nose and using the entire shell casing as a ground plane, they created an antenna system that was built into the projectile itself. The transmitter design went through dozens of iterations during the summer of 1941. Engineers working in Carnegie Institution's basement laboratory hand-soldered circuits, potted them in waterproof resin, mounted them inside dummy shell casings, and sent them to Aberdeen for firing tests. The failure rate was discouraging. Shells would fire successfully, but when recovered downrange and examined, the circuits were usually destroyed. Solder joints cracked, components broke loose. Resin potting crumbled under shock. By September 1941, after 10 months of development and roughly 400 test firings, Tuve's team had achieved a functioning prototype that survived firing approximately 40% of the time. That was nowhere near the reliability needed for combat use, but it proved the concept was achievable. The transmitter could broadcast. The receiver could detect reflections. The triggering circuit could fire a detonator. Everything worked in principle. Making it work consistently required manufacturing precision that didn't exist in 1941. Then Pearl Harbor happened, and suddenly the proximity fuse wasn't an interesting research project. It was a desperate priority. Japanese aircraft carriers had just demonstrated that air power could cripple naval forces, and American anti-aircraft defenses were using the same primitive time fuses and contact fuses that were failing British gunners over London. The Navy's Bureau of Ordnance contacted Tuve in December 1941 with an urgent question. How soon could proximity fuses enter production for anti-aircraft use? Tuve's honest answer was 2 years minimum, assuming they could solve the reliability problems and scale up manufacturing. The Navy gave him 18 months and unlimited funding. What followed was one of the most intense engineering programs of World War II, a crash development effort that would eventually employ more than 7,000 scientists, engineers, and technicians working at laboratories across the country. Tuve established the Applied Physics Laboratory at Johns Hopkins University in March 1942 to coordinate the work. APL became the hub for proximity fuse development, but the program stretched far beyond one laboratory. Western Electric designed manufacturing equipment. Eastman Kodak developed photographic quality control methods for inspecting miniature components. General Electric contributed power supply designs. Dozens of smaller companies fabricated specialized parts and contracts that never explained what the components were actually for, just that they had to meet extraordinarily tight tolerances. The reliability problems broke down into dozens of smaller technical challenges. Vacuum tube filaments still failed too often, so Raytheon redesigned the mounting system 3 times. The battery that powered the circuit needed to remain inert during storage, then activate instantly when the shell was fired, so engineers developed a spinning reserve battery that used centrifugal force from the shell's rotation to force electrolyte into contact with battery plates. The detonator circuit needed to distinguish between genuine target reflections and false signals from ground clutter or rain, so designers added discriminator circuits that only triggered when the received signal strength increased rapidly, indicating the shell was closing on a target. Every component had to be miniaturized. The complete fuse assembly had to fit inside the nose cone of a Feynman, 5-inch naval gun shell, occupying a space roughly 4 inches long and 3 inches in diameter. Within that space, engineers packed 4 vacuum tubes, a battery, a transmitter circuit, a receiver circuit, an amplifier, a discriminator circuit, a safety arming mechanism, and a detonator. The entire assembly weighed 22 ounces. Testing protocols became increasingly elaborate as the program matured. Early in development, shells were simply fired at Aberdeen Proving Ground and recovered to see if the circuits survived. By mid-1942, APL had established a comprehensive test regime. Every fuse design underwent vibration testing to simulate the shaking during shell transport. Temperature cycling tests exposed fuses to extremes from -50 to +140 degrees Fahrenheit. Humidity tests soaked fuses in tropical moisture conditions. Drop tests simulated rough handling. Only after passing all those preliminary tests would a fuse design be loaded into a shell and actually fired. Even then, the test firings happened in stages. First, static firings where the shell was secured in a test fixture and the gun fired to generate acceleration forces without the shell actually leaving the barrel. Engineers could examine the fuse immediately after firing to document exactly what failed. Next came live firings at test ranges where the shells flew actual trajectories, but over controlled environments where every shell could be recovered and examined. Finally came proximity tests, where shells were fired past target drones to verify the fuses would actually detect aircraft and detonate at the correct distance. The target drones were radio-controlled aircraft towed by cables behind bombers flying at varying altitudes and speeds. Getting all of this right took until the spring of 1943. The first combat-ready proximity fuses, designated VT Mark 32, entered production in April 1943 at a Western Electric facility in New Jersey. The manufacturing process was unlike anything Western Electric had attempted before. Workers assembled fuses in clean rooms with filtered air to prevent dust contamination. Each vacuum tube was individually tested before installation. Solder joints were inspected under magnification. Completed fuses underwent X-ray examination to verify proper component placement. Every single fuse was tested electrically before being approved for loading into shells. The reject rate ran close to 30% in early production, meaning 3 out of 10 fuses failed quality control and had to be scrapped or reworked. By the summer of 1943, Western Electric was producing roughly 3,000 proximity fuses daily. The Navy began issuing them to ships operating in the Pacific, though under extraordinary security restrictions. Shells fitted with proximity fuses were stored separately from conventional ammunition and marked only with inconspicuous coded labels. Gunners weren't told how the fuses worked, just that they should expect better performance against aircraft targets. Ships carrying proximity fuse ammunition received orders to fire them only over water, never over land where unexploded shells might be recovered by enemy forces. The security paranoia was justified. If German or Japanese engineers captured an intact proximity fuse and reverse-engineered the technology, they could deploy their own versions, potentially neutralizing the Allied advantage. More frighteningly, they could develop countermeasures, radio jamming systems that would prevent the fuses from functioning. The fuses first entered combat during the Guadalcanal campaign in August 1943, when Japanese aircraft attacked American naval forces supporting the Solomon Islands operations. Gunners aboard the USS Helena fired 5-inch shells equipped with proximity fuses at attacking bombers. The results were dramatic enough that the ship's after-action report had to be sanitized before filing because the hit rates seemed impossible. Helena's gunners claimed 7 aircraft destroyed with just 43 shells fired, a ratio that would have been unthinkable using conventional time fuses. Subsequent Pacific naval engagements confirmed the pattern. Ships equipped with proximity fuses consistently achieved aircraft kill rates 3 to 4 times higher than ships using conventional ammunition. During the Battle of the Philippine Sea in June 1944, American ships fired roughly 60,000 anti-aircraft rounds and destroyed approximately 400 Japanese aircraft. Analysis suggested that proximity fuse ammunition accounted for roughly half the kills, despite representing only 20% of rounds fired. Japanese pilots began reporting their surprise that American anti-aircraft fire seemed impossibly accurate, with shells exploding directly alongside their aircraft, even when they maneuvered violently. Technology remained so secret that American gunners themselves weren't fully briefed on how it worked until mid-1944. Most assumed it was some kind of improved time fuse with better precision. The Navy and Army Ordnance Department feared that if gunners knew the fuses used radio technology, they might inadvertently reveal that information if captured. Only officers at the battalion level and above received detailed briefings, and those officers were under orders to never mention proximity fuses in any written communication that might be intercepted. The security measures extended to manufacturing. Workers at Western Electric and other contractor facilities weren't told what the devices they were assembling actually did. They knew they were building components for artillery fuses, but not that those fuses contained radio transmitters and receivers. Compartmentalized production meant individual workers assembled small sub-assemblies without seeing the complete fuse. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Only, final assembly technicians and quality control inspectors handled complete units, and they worked in restricted areas requiring special clearances. Despite all precautions, the Germans eventually figured out something unusual was happening with American artillery. Luftwaffe intelligence officers analyzing combat reports from late 1943 noted that American anti-aircraft fire was becoming suspiciously effective. German scientists theorized that the Americans might have developed some kind of radio-based fuse, but they assumed such a device would be too large and fragile to survive artillery firing. German attempts to develop their own proximity fuses stalled in early development, when test firings consistently destroyed their experimental circuits. By the autumn of 1944, proximity fuse production had expanded dramatically. Multiple manufacturing facilities were producing roughly 40,000 fuses daily, enough to supply both naval anti-aircraft guns and Army artillery units. The original VT Mark 32 design, intended specifically for 5-inch naval guns, had been adapted into variants for 75mm, 90mm, and 105mm Army artillery pieces. Each caliber required slightly different fuse dimensions and different acceleration tolerance, because smaller shells experienced higher G-forces during firing. The 105mm proximity fuse, designated VT Mark 53, would become the version that changed ground warfare during the Battle of the Bulge. It was designed to fit the standard 105mm howitzer shells used by American field artillery battalions supporting infantry divisions. The adaptation from anti-aircraft use to ground support role wasn't obvious. Proximity fuses had been designed to detect aircraft, large metal targets moving through empty sky. Ground targets presented entirely different challenges. Infantry and vehicles were smaller. They were surrounded by terrain clutter that could generate false reflections, trees, buildings, hills. The fuses needed to ignore ground reflections while still detecting troops in the open, a discrimination problem that required modifying the receiver circuits to filter signals based on reflection strength and rate of change. Testing ground support proximity fuses began at Aberdeen Proving Ground in the summer of 1944. Engineers set up realistic battlefield scenarios with mock infantry positions, trenches, and vehicle targets spread across test ranges. Artillery batteries fired shells equipped with prototype fuses, while observers documented where the shells actually detonated and what damage resulted. The optimal burst height turned out to be roughly 40 to 60 feet above ground. Higher bursts scattered fragments too widely, reducing casualty density. Lower bursts concentrated fragments but reduced the coverage area. 60 feet provided the sweet spot where a single shell's fragmentation pattern could effectively suppress infantry across an area roughly 75 yards in diameter. By November 1944, the VT Mark 53 had passed all tests and entered production for ground use. The timing was extraordinarily fortunate. German forces were preparing their final major offensive of the war in Western Europe, and American artillery was about to face its most demanding test. The Battle of the Bulge erupted on December 16th, 1944, when 3 German armies smashed through thinly held American positions in the Ardennes forest. The attack achieved complete tactical surprise, catching American forces dispersed and unprepared. Within 48 hours, German panzers had advanced 20 miles, surrounding the critical road junction at Bastogne and threatening to split the Allied front. The 101st Airborne Division, rushed to Bastogne from reserve positions, found themselves encircled by December 21st. German forces outnumbered the American defenders roughly 4-1, and the Luftwaffe had achieved temporary air superiority, grounding Allied close air support. Artillery was the only thing preventing German infantry from overwhelming American positions through sheer numerical advantage. The problem was ammunition. The 101st had arrived at Bastogne with minimal supplies, expecting to be reinforced quickly. The German encirclement cut supply lines, leaving American gunners with dwindling shell stocks. Every round had to count, and conventional ammunition wasn't delivering the effectiveness the defenders desperately needed. German infantry attacked in dense formations, trying to overwhelm American positions through concentrated mass. Traditional time fuses required gunners to calculate precise burst heights for each target, a time-consuming process that German forces exploited by maneuvering constantly, changing their positions and directions to make those calculations obsolete. Contact fuses were nearly worthless because the Ardennes landscape was covered in 2 feet of snow. Shells buried themselves in snow and frozen ground before detonating, producing impressive craters but minimal casualties against above-ground targets. Artillery officers at Bastogne sent urgent requests for any available ammunition, specifying that they needed something more effective against massed infantry. Supply officers back at ordnance depots made a decision that would change the battle's outcome. On December 22nd, C-47 transport aircraft loaded with ammunition flew through terrible weather to airdrop supplies to the surrounded defenders. Among the supply bundles were 5,105 mm shells, equipped with VT Mark 53 proximity fuses. The shells came with minimal documentation, just instructions that gunners should fire them like normal rounds, but expect detonation before impact. No detailed explanation of how the fuses worked. No special handling procedures beyond what was printed on the shipping crates. Gunners of the 327th Glider Infantry Regiment's attached artillery battalion were the first to fire proximity fuses in ground combat on the Western Front. Lieutenant Colonel Paul Danahy's after-action report, written 3 weeks later, described the experience with barely contained amazement. His battery had been engaging German infantry, advancing across an open, snow-covered field, roughly 2,000 yards from American positions. Using conventional time fuses, Danahy's gunners were achieving marginal results. They'd fire, observers would call corrections, and by the time the next salvo arrived, German troops had shifted positions. Danahy ordered his battery to switch to the new VT-fused shells, though he admits in his report that he had no clear understanding of what made them different. His gunners loaded, aimed, and fired. The shells detonated approximately 50 feet above the German infantry, creating airbursts that carpeted the entire target area with fragmentation. The effect was devastating. German forces that had been maneuvering aggressively suddenly stopped, broke formation, and retreated. Danahy's observers reported that the German infantry appeared shocked, unable to understand why American shells were suddenly exploding directly above them without warning. For soldiers accustomed to diving for cover when they saw shell impacts, the proximity fuse offered no defense. There was no impact warning, no chance to take cover. The shells simply detonated overhead, and fragments rained down before anyone could react. Over the following week, as more proximity fuse ammunition reached Bastogne defenders, the tactical situation stabilized. German infantry attacks that should have succeeded through numerical superiority were broken up by artillery fire that was suddenly 4 times more lethal per round fired. American gunners who'd been rationing ammunition because supplies were scarce found that they could achieve decisive effects with fewer shells. One battery commander reported stopping a German attack of approximately 200 infantry, using just 36 proximity-fused shells, whereas previous engagements against similar targets had required over 150 rounds of conventional ammunition. The psychological effect on German troops was profound. Veteran Wehrmacht soldiers who'd survived years of combat on the Eastern Front reported that American proximity fuse artillery was more frightening than anything they'd encountered, including Soviet Katyusha rocket barrages. The unpredictability was uniquely disturbing. Soldiers couldn't hear shells approaching, couldn't see them coming, and had no time to react when they detonated. Several German prisoners interviewed after the battle specifically mentioned the overhead bursting shells as the reason they'd abandoned their positions. By early January 1945, as Allied forces counterattacked and relieved Bastogne, proximity fuse ammunition had become standard issue for American artillery across the European theatre. Production facilities were manufacturing 90,000 fuses daily, and stockpiles were being shipped to every field artillery battalion in the European theatre of operations. The original security restrictions remained in place. Shells could only be fired in situations where unexploded rounds were unlikely to fall into enemy hands, but commanders interpreted those rules loosely given the demonstrated effectiveness. German intelligence services eventually recovered several unexploded proximity fuse shells in January 1945. Engineers at the Waffenamt, Germany's weapons development agency, examined the fuses with reported astonishment. The miniaturization and ruggedness of the components impressed them, but by that stage of the war, Germany lacked the industrial capacity and materials to develop competing technology. Vacuum tube production in Germany was focused on radar and communication equipment. There was no possibility of diverting resources to proximity fuse development when the Reich was collapsing. The final accounting of proximity fuse effectiveness came from post-war analysis conducted by the US Army's Operations Research Office. Examining combat data from late 1944 and early 1945, researchers calculated that proximity fuses increased artillery effectiveness against infantry targets by approximately 300%. That meant American forces achieved the same suppression or casualty effect using 1/3 the ammunition they would have needed with conventional fuses. In practical terms, this translated to lives saved on both sides. American infantry advancing behind proximity fuse artillery barrages faced less resistance and took fewer casualties because German defensive positions were more effectively suppressed. German casualties were actually lower in some engagements because proximity-fused artillery convinced German troops to surrender or retreat rather than fighting to the last man against overwhelmingly effective firepower. The proximity fuse also validated a controversial decision the Roosevelt administration had made in 1942, prioritizing basic scientific research during wartime. Many politicians and military officers had argued that wartime R&D funding should focus exclusively on incremental improvements to existing weapons. Why waste money on speculative technologies like proximity fuses, when that same funding could produce more tanks or aircraft using proven designs? The Tuve program demonstrated that breakthrough technologies could deliver strategic advantages that incremental improvements never would. The $300 million invested in proximity fuse development, equivalent to roughly $5 billion in 2025 dollars, bought a capability that no amount of conventional ammunition could have matched. Beyond its direct military impact, the proximity fuse program established organizational precedents that shaped post-war American defense research. The Applied Physics Laboratory model, bringing together university researchers, private industry engineers, and military end users in coordinated development programs, became the template for projects ranging from guided missiles to nuclear weapons. The tight integration between research, testing, and production that Tuve had pioneered at APL influenced how the Pentagon structured major weapons programs for decades afterward. The personnel who worked on proximity fuses went on to dominate American physics and engineering through the Cold War era. Over 200 veterans of the APL proximity fuse program later worked on the Manhattan Project. Others moved into guided missile development, radar systems, early computer design, and eventually the space program. The technical skills they'd developed, miniaturization, ruggedization, systems integration under extreme constraints, became foundational capabilities for American technological superiority in the second half of the 20th century. Merle Tuve himself returned to pure scientific research after the war, directing the Carnegie Institution's Department of Terrestrial Magnetism until his retirement in 1966. He rarely discussed his proximity fuse work publicly, uncomfortable with the fact that his most famous achievement involved weapons. In one of the few interviews he gave about the project, recorded in 1971, Tuve reflected on the paradox of scientists contributing to warfare. He noted that the proximity fuse probably saved more lives than it took by shortening battles and convincing enemy forces to surrender rather than fight hopeless engagements. Whether that moral calculation actually balanced, Tuve admitted he couldn't say. The technology itself continued evolving long after World War II ended. Modern proximity fuses use solid-state electronics and microprocessors instead of vacuum tubes, laser or radar sensing instead of simple radio reflection, and sophisticated discrimination algorithms to distinguish targets from clutter. But the fundamental concept remains unchanged from what Tuve's team developed in 1941 through 43, a shell that senses when it's near a target and detonates automatically at optimal distance. The proximity fuse represented something unusual in military technology history. Most weapons innovations involve making something more powerful: a bigger bomb, a faster aircraft, thicker armor. Tuve's team did the opposite. They made something smarter. They took an existing weapon, the artillery shell, and gave it the ability to make one critical decision on its own: when to explode. That single autonomous decision, made by circuits no more sophisticated than a basic radio, changed how wars were fought, and it established the principle that would eventually dominate 21st century warfare. Precision and timing matter more than raw firepower. When the last veteran proximity fuse shells were finally retired from U.S. military service in the late 1980s, replaced by laser-guided and GPS-guided munitions, they'd been in continuous use for over 40 years. More than 22 million proximity fuses had been manufactured during World War II alone. Post-war production for Korea, Vietnam, and Cold War stockpiles added another 18 million. No other weapons technology from the 1940s remained frontline equipment for so long. The reason was simple. Tuve's team had solved the fundamental problem correctly the first time. They'd built something that worked reliably under the most extreme conditions imaginable, and no subsequent technology could improve on the basic concept enough to justify replacing it. Sometimes the first brilliant solution is also the lasting one. The kitchen timer fuse that let US shells explode inside German positions wasn't really a timer at all. It was something far more sophisticated, disguised as something simple. A radio that could survive being shot from a cannon, sense the presence of enemy forces, and execute its single deadly purpose with reliability that would have seemed impossible just a few years earlier. That Merle Tuve and his team achieved this, starting from essentially nothing, working under impossible deadlines with immature technology, remains one of the most impressive engineering accomplishments of World War II. More importantly, it was an accomplishment that saved countless lives on all sides by ending battles faster and more decisively than would have been possible otherwise. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.